Hi there, it's Miss Adams from Flamingo Math. We're in day 2 for lesson 13 in unit 2. We're still solving log equations and inequalities. Today's lesson is going to be about some more difficult types of equations and a few application problems. Our third lesson will be on the inequalities. In example 9, we want to support our answer graphically as well as algebraically. So I like to teach the fact that I see a quadratic equation here. I'm going to let u be represented as e to the x because what I'm seeing here is e to the x gets squared and then negative 3e to the x and then minus 4. So I see that equation like a quadratic problem. And I can factor u squared minus 3u minus 4 because 4 times 1 is 4 and negative 4 plus 1 would give us that negative 3 term in the middle. So it's very simple that we can get u equals 4 and u equals negative 1. So we want to think back. Our substitution was e to the x. So if we return u as e to the x equals 4 and e to the x equals negative 1, you can right away see this isn't possible. It's going to be an extraneous solution. But e to the x equals 4, if we take the natural log of the left and the natural log of 4, we can bring that x in front and say natural log of e is natural log of 4. And the natural log of e is 1. So 1 times x is x. And x is natural log of 4. And this is our exact solution. Using a calculator, an approximation for natural log of 4 is about 1.386. So we have two different types of solutions depending on how you need it, and we're asked to verify or support that answer graphically. And using my graphing calculator off screen, I see a graph that looks something like this. And using the zero finder, I see that it is that approximation 1.3860. Let's go try example 10. Okay, example 10 is a little more complicated. We want to multiply both sides by 2, so e to the x minus e to the negative x is 16. And if we, let's think about this, if we let u equal e to the x, and we multiply both sides by e to the x, we can create a quadratic where we have e to the 2x minus e to the 0 is 16 e to the x. And by substituting u for e to the x, we have u squared minus 1 is equal to 16u. So collecting like terms on the left, that cannot be factored, and we could use the quadratic formula. So u is equal to opposite b plus or minus the square root of b squared. B is 16. 16 squared is 256. Minus 4 times a is 1, and c is negative 1. So using the discriminant there, divided by 2 times a, which is 1. So combining like terms under the radical, we got 16 plus or minus the square root of, 256, 260, and that divided by 2, so 8, grab my calculator real quick here. Square root of 260 is 2 square roots of 65, and we're dividing by 2, and then 16 divided by 2, so I'm going to erase all of that. And we end up with 8. 16 divided by 2 is 8, plus or minus the square root of 65. Now remember, u is e to the x, so we need to come back and substitute e to the x is 8 plus or minus the square root of 65. So to get the exact answer, we want to take the natural log of both sides. So the natural log of e to the x is just x, and the natural log of 8 plus or minus the square root of 65 is the right. Now, it should be obvious that the only appropriate answer, or the only answer that's not extraneous, would be the positive result. So we don't need the negative result. That would be our exact answer. And using the calculator for an approximate answer, natural log of the quantity 8 plus radical 65 is about 2.776, because the minus is not a real answer. That would be extraneous. And then to back that up with a graph, we can look at the graph on our calculator. This is my x-axis, this is y. The graph looks something like this, and then y equals 8 is going across horizontally right there. That solution is 2.776 when y equals 8, and that does match our two answers, both exact and approximate. In 11 and 12, we're going to look at the same type of feature where there's quadratic type log equations. So multiplying the left side natural log of 3x minus 2 times x minus 1 is equal to the natural log of x squared. When the logs are the same, so the natural log on the left and the natural log on the right, that tells us that our arguments are equal. Setting the arguments equal and multiplying or distributing 3x minus 2 times x minus 1, we get 3x squared minus 5x plus 2 is equal to x squared. Collecting like terms, 2x squared minus 5x plus 2 is equal to 0. This does factor. 2x minus 1 times x minus 2. And here we have x equals 1/2 and x equals 2. So we've got to go back and check. It looks like we can't substitute 1/2 into this second term. That would be extraneous. It works okay in the other two, so this one is extraneous. And x equals 2 would be a valid solution for all three terms. That's our only solution. Moving on to example 12, log base 3. So we have log base 3 on the left, and we are going to multiply x times x minus 8. That's equal to 2. So log base 3 x squared minus 8x is equal to 2. And that's true when x squared minus 8x is equal to the base raised to the power 2. So x squared minus 8x minus 9 is equal to 0 when x minus 9 times x plus 1 is equal to 0. X equals 9, go check that. It works in this term and this term. We're taking positive log, but x equals -1 would not work. We can't have the log of a negative value, so this would be an extraneous solution. Example 13 should be an application problem. You deposited $1,000 in an account that pays 6.5% interest. It's compounded continuously, and you can find the balance in your account using the formula A of t is 1000 e to the 0.065 t. We want to find a formula that requires for the balance in your account to double. So doubling 1000 would be 2000. 2000 is 1000 e to the 0.065 t. If we divide by 1000, then 2 is e to the 0.065 t. Take the natural log of the left and the right. The natural log of 2 is e to the 0.065 t. This is 1. This comes out as a factor in the front. So natural log of 2 is 0.065 t. Dividing by 0.065, natural log of 2 divided by 0.065 is t. As a decimal, that's about 10.664 years. So in the 11th year, your money's going to double. And you can check that using your graphing calculator. Here we want to find the inverse of A and explain the meaning of this inverse in context. So to get the inverse of A, we're going to replace the y value with t, and we're going to place the t value with A, and then we're going to solve for A. So t divided by 1000 is equal to e to the 0.065 a. If we take the natural log of 0.001 t, I'm just changing this 1 over 1000 to a decimal, and that's going to be the natural log of e to this power. So we've got A is natural log of 0.001 t divided by 0.065. This is our inverse, so we're going to rename it A inverse of t is natural log of 1,000th t divided by 0.065. What does A inverse of t mean? It tells me the year when a balance in an account is known. So if you know the balance in the account is $5,000 and you substitute it in there, then you could figure out the year that happened. Let's go graph A inverse with the scale on the x-axis from 0 to 3,000 and the y-axis from 0 to 20. So we have 1,000 in the first year. Let's see, 1,500 is a little more than 6, 2,000. It's a little more, so we've got a graph going across here, A inverse, and we want to know when is the inverse 1,500, and it looks like there's $1,500 in the account at about 6 1/4 years. So this would be, let's see, let's label this axis. This would be the amount in dollars. And the y-axis would be the time in years. So what did we find out? The account balance will reach $1,500 $1,500 in about 6.24 years. So it's a quarter of the way through the 7th year. And then example 14, equations that involve combinations of exponential or log functions or algebraic functions can be difficult to solve. So we're going to take advantage of technology here. And I'm going to ask you to get your calculator out. E to the 2x equals 60. I found e to the 2x at 1.8 is 36.60. At 1.9 is 44.70. At 2, 54.60. At 2.1, we've reached over what we're looking for. Our target is 60, 81.45. So we're looking for e to the 2x is equal to 60. We're looking for that intersection point. Where is that? If this is x, and this is y, and this is 60, and this is 2e to the 2x power. So on 2 to 2.1, x is about 2.047. So what I did was I zoomed in between here and looked at trace, and then I used the intersection feature and found that location. Let's look at B. For 2 log base 3 of 1/2 x equals 3. And again, I'm looking at the graph here using my graphing utility. I see this is my log graph, and this is y equals 3, and I'm looking for that intersection point right there. Where is that located? Because I've got 2.52 when x is 8, 2.74, 2.93. This is 3.10, so it's somewhere between 10 and 11 and 3.26. So we know the interval is on some number between 10 and 11. And when I used that intersect feature, I found out x was 10.392. So being able to do that with your calculator is an important skill. And then lastly, we want to solve algebraically and check our results on a graphing utility. This is similar to one we did earlier, where we're going to multiply both sides by 2. So 3 to the x minus 3 to the negative x is 5 times 2, that's 10. If I multiply the left and the right by 3 to the x, 3x minus 3 to the negative x, and this one times 10, I can create that quadratic. So 3 to the 2x minus 3 to the 0 equals 10 times 3 to the x. And then we want to let a u substitution represent 3 to the x. So we have that quadratic, u squared minus 1 equals, what, 10 to the u. So bringing those terms together on one side, that is not something that you can factor. So we're going to be forced to use the quadratic formula and solve in terms of u. U is opposite b plus or minus the square root of b squared minus 4 times a times c, all divided by 2 times a. So u represents 3 to the x, and that looks like, 10 plus or minus the square root of 104 divided by 2. So if we take log base 3 of the left-hand side, let's come up here, log base 3 of 3 to the x, we're just going to end up with x on the left. And then we've got log base 3. And I'm going to go to the calculator and figure up this portion. 3 to the x looks like 10.0990. So we got log base 3 of 10.0990. So x, this is the exact answer. That's the exact answer. Log base 3 of 10.099. And then our approximate answer is 2.10487. I can round that, 2.105 if you want. And then checking with the calculator just to finish up the question. This is my y-axis. This is our x-axis. We're graphing the original function, 3 to the x minus 3 to the negative x over 2. Looks like that. Then we're graphing y equals 5 for the right-hand side. This is the left-hand side, 3 to the x minus 3 to the negative x over 2. And that intersection point is 2.105, bingo, comma, 5. So we have checked that out. And my friends, that is the end of lesson day 2 in 1213. I forgot to mention that I threw away that negative answer, but we know that u can't be 10 minus 104 under the radical divided by 2. That's a not real number. One more day on this lesson. It's all about inequalities. Come check it out tomorrow.